Okay, so in working on maze solving and implementing backtracking rather than randomly walking through a maze, which is not an efficient approach, of course. Backtracking is generally this algorithmic approach that consists of using a recursive function. So a nice, simple, relatively simple example of recursion is in converting a decimal number to a binary number. So the one approach to an iterative way of converting decimal to binary is here. While the decimal number is greater than 0, we divide by 2, and before that we printed decimal number mod 2. We pushed it into an array of integers. And then I reversed the array of integers, and I'm also adding padding zeros here. So just to go through this case first, if we have 42, the binary equivalent of that is 0, 0, 1, 0, 1, 0, 1, 0. So this is the ones place, the twos place, fours place, eights place, 16, 32. So 32 times 1 is 32, plus 8 times 1 is 40, plus 2 times 1 is 42. Okay, so in that iterative process, we took 42 divided by, first we printed 42 mod 2, which is equal to 1, and excuse me, it's equal to 0. That is that 0 right there. Then we had that while loop condition, which ran while this number is um, greater than 0 or not equal to 0, greater than 0. So we did this division. So 42 integer divide 2 is 21. Then we printed 21 mod 2, which was equal to 1. That is that one right there. Then we have 21 integer divide 2 is equal to 10, 10. So then we printed 10 mod 2, 10 mod 2, which is equal to 0. That's that 0 right there. So we've printed 0, 1, 0, 0, 1, 0. And then we have 5 mod 2, which is equal to 1, because we said we stored the new decimal number. We updated it with saying decimal number equal 10 divided by 2. So we got 5. Okay. And then we have 5 integer divided by 2, or 5 mod 2 is equal to, um, I didn't mean to get into this amount of detail as usual. Okay, so that works for the iterative approach. The recursive approach should, of course, produce the same output. Um, I did do that reversal of digits in this case, which is, I'm sure, not optimal. Okay, so convert recursively. The base case that is going to terminate the recursion, so we don't have infinite recursion, is the decimal number is equal to 0. So not greater than 0 in this case, but equal to 0. And I printed done here, which is a little bit silly, but that's okay. The recursive case is the event that the decimal number is greater than 0 in this case, assuming you feed in a positive value. Maybe this should be an unsigned integer or size t. Okay, so just an interesting thing that I wanted to point out here. So the decimal number is 42 in this example case. So again, the binary equivalent is, I like to do groupings of 4 so I can read the number 0, 0, 1, 0, 1010. So let's see what we get in this case. This was my brain's natural inclination to use this approach, but if we switch the order of lines 52 and 54, it's one of the interesting things in recursion. So I wanted to step through that. But let's see what we get first. If we call the function, of course. We got our decimal number, and then we call convert decimal to binary recursively. For the iterative approach, I stored the binary equivalent as a vector of integers. So for the recursive approach, I'm not storing the data in a vector of integers. Maybe I'll update that in a bit. Okay, so the return type is void here. It takes a decimal number, which is an integer. Okay, so if we run this, do we see this? Or some, I didn't add any padding here, so I didn't call this function up above, which is add padding zeros, which, well, the size is not equal to 4, is not a multiple 4, we push back zeros. Okay, so do we see this? We see, there's that done right there at the end. We see 0, 1, 0, 1, 0, 1, 0, 1. So we're actually looking at this in reverse. So we're not seeing this leading digit right here, the leading 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's not what we're looking at here. Instead, we're looking at 1, 2, 3, 4, 5, 6. So this one right here is this one. So we printed the number in reverse, and if we paste that print statement after the recursive call, so we're going to print done first as the first bit of text output. So done is going to appear left as the leftmost thing here. So this is interesting, and it's similar to L in R versus R in L traversal in binary trees. So now we print 1 0 1 1 1 0 1 0 1 0 0 1 0. So we're printing in the correct order here. Shouldn't have a leading 0 in this case unless we added padding, which we didn't. And in this case, it should have 2 leading zeros if we wanted that to go to that style. So I wanted to step through this and set a breakpoint and be looking at local variables and return. There are no return values in this case. The return type is void. So let's set a breakpoint right here, I suppose. Yeah, so copies of this decimal number are going to be maintained on a function call stack. I just wish I could sort of interrogate the function call stack with recursion using debugging tools. I'm sure there's some way. I just haven't discovered it yet. So here's our local variables. And initially decimal number is 42. So that's not equal to 0, so we're not done yet. And in this case, done is misleading. Okay. In a way. Okay, so we call convert decimal to binary recursively with 42 divided by 2, or 21. So we're not going to step to line 54. We're going to step back up to the function call. And let me, I guess, show the function call stack so we can see it grow, although the value of this is not been as great as I was hoping when I first discovered the tool. Yeah, what I'm wanting to do is be able to um, click some option here that expands and shows all the data that's maintained in a function call. Something like getting into assembly. Okay, so we are at this line, so we're going to call again, and we're going to see the function call stack grows. We main called this function, and this function is about to call itself. Okay, so we added a call, and let's see, local, where are locals? Local variables, decimal number is 42 at the moment, but it's about to become, once we, this one window, one screen business is unpleasant sometime in this case. Okay, so we're about to step inside the function definition and we'll see the decimal number gets updated. Updated to 21. 21 is not equal to 0. We call 21 divided by 2 is 10. Okay, and still we haven't printed anything yet. If we look at the terminal here, we see nothing. Just a blinking cursor. Okay, so becomes 10. 10 is not 0. 5 is not 0. 2 is not 0. 2 divided by 2 is 1. 1 is not 0. And the function call stack has grown to like 5 or 6 calls. This has called itself 1, 2, 3, 4, 5 times. And we also have the values of the decimal number here in parentheses, so that's kind of convenient. I guess some confusion may come in if I return a vector of integers or return a single integer, which I should modify this in a bit, see how that goes. Okay, so I think we were at 1. Yeah, decimal number is 1, so we're not done yet. 1 integer divided by 2 is 0, so 0 is 0. And 0 is 0, so we're going to print done. Done. Okay. There it is in the terminal. And now we'll see the popping of the function call stack. So we have 42 and the 0, so this is going to get popped, and we're going to step back to line 54. And the value of decimal number is going to be 1. So we should see the local variable value gets updated to 1. And we're going to print C out 1 mod 2, which is 1. 1 divided by 2 is 0 with a remainder of 1. Okay. Where's our arrow? Okay, we printed done. All right. Now we'll step from here to this from this close brace to the close brace of the function call. Okay. And then we pop the function call stack and this topmost entry disappears. Okay, the 0 disappeared and now we have the 1. And so now the value of decimal number is 1, as we can see in the local variables. So we print C out 1 mod 2, which is 1. So we got done and then 1. Step. And if we print it, yes. Okay. So we step to the end of this instance of the function call. And the function call stack will get popped. And we've got 2 now, and we're back at the print statement. And we got the 2 mod 2 is 0, so we're going to print a 0 here. Yes, okay. Just to quickly get through this, now we're going to pop the function call stack, or to speed up a little bit, we pop. Now we got 5. 5 mod 2 is 1. We're going to print 1. Okay, so step, pop, printing 0 now. We printed the 1. Just not keeping up properly. Okay. And finally, we returned zero because I went a little quicker than I intended. Okay, this makes good sense. Doesn't seem particularly useful in this case, but in the instance of tree traversal and depth first search, it is more useful. Depth first search on graph data structures also. So what happens if we just to hold on to that because I'm about to make substantial changes. Maybe we just copy this and make an overload that returns an integer. And just forget the rules on that. Overload, function overloads. Okay. So maybe return like a leading zero here, which is a bit misleading. Otherwise, so usually might see this. I'm just poking around and seeing what happens here. Okay, I'm gonna ignore the return value and just see what we get. Well, let's print the return value. Okay, so is this an equivalent approach? Let's take a look. So 42 is not zero, so we're not going to return zero. So we step to the recursive case, and this returns a function call. Okay, I thought I needed to change my function name for a minute there because it's a different function. So we return decimal number divided by 2. So return a call with 21. And again, we'll see the function call stack grow. So we step. Okay. And get updated to 21. 21 is not 0. And what do we look? So in the base case, let me just continue. Okay, 21 and then 10. Eventually, we're going to return 0. So is this going to be a wall, just a wall of zeros, so to speak? Haven't printed anything yet, of course, because the main function is the only thing that does any print. Not 0, not 0, 1, and now 0. So we return 0, and let's in the locals window pane down here, I believe it usually mentions the return value. So we return 0, and then we step back to this return statement. And we also pop the function call stack. So we step back to, so we're at the end of the function definition. We see what it recursively returned a bunch of zeros. Okay. And we're going to see 0 here. So it's so there's no mod operator here. So obviously this can't be the right approach. So return decimal number plus this whatever this decimal number mod 2. Silly me not to notice that before, of course. Okay, let's take another look. We're not going to see what it returned until we hit the base case, so I kind of want to fool around with that. Conditions, sure. Conditions, decimal. I think that's the double equals is used here. Okay, so this condition is saved. Stop, so I don't have to step through multiple times. Okay, decimal number is 0, so it looks like that worked correctly. Our function call stack should have 5 or 6 calls in it. Okay, and 42, 21, 10, etc. So we return 0 initially, so that's going to be this value here. And the decimal number up above is 1 mod 2, so. And it's not addition, it's concatenation in this case. It should be concatenation, like adding. Let's just see if we're getting the digits right at any rate. I'm mixing up, like if this were a converting binary to decimal program, this is the kind of thing we would do. I was interpreting addition as more like we have a 0 and now we add a 1. As a string. Okay. All right. Decimal number is 0, or is it 1? 0, so we return 0. Okay. And we'll also see the return value here in locals. Okay, return 0, 65, line 65 gets executed. We come to the close brace of function definition, this call. So we should see returned 0 here. Recursively return 0. And that gets, oops. Now we come back to this statement. So the return value here, this thing was 0. And the decimal number is 1 because that was the thing above it, or down below the 0 call with 0 on the function call stack. I'm having a devil of a time with my single screen here. Okay, so 0 plus 1. Again, it's not plus 1 in this case, so that's going to be confusing. And what's the alternative? It's going to get interpreted as integer division, so that's silly. But I don't know, maybe there's some value in continuing. So this is going to return 0 plus 1, which is 1. It's not going to produce the right answer, but okay. Now decimal number is 2, but in fact it should be 1, 0. It seems too silly. Let's return a string, I suppose. Now this will, can we convert to a character here, and maybe we're printing it in reverse, but character equivalent of this guy. So the so does this need to be lowercase a is 97 in ASCII? So do we need to add, do we need to look up an ASCII table? And we're going to be returning either 0 or 1. So the character or the symbol 0 or 1 has decimal value 48 and 49. So do we need to add 48 before we do this cast? Let's just see. Okay. So this should get interpreted as concatenation of a character to strings. Okay. Maybe. We'll return the string 0. Okay. I returned the string 0. Return. Okay. Now we are at decimal number 1. So 1 mod 2 is 1. 1 plus 48 is 49. So that should be the character, the string, the character 1, not the number 1. Okay. And we concatenate that number 1 with the number previously returned, which was 0, 1, 0. So do we now see 1, 0 as the return once we get to the end? Okay, return 1, 0. Now the decimal number is back to 2. If we look at the function call stack, which I moved to my other screen here, we have 1, 2, 3, 4, 5 left to go. Okay, so 2 mod 2 is 0, so we should return the string 0, 1, 0, 0, 1, 0. Okay, that's good. We might need to reverse the string at the once we return it to the main function, or yeah. Okay, now decimal number is 5. 5 mod 2 is 1. We're gonna have 1, 0, 1, 0. And okay, 1, 0, 1, 0. And okay, this seems to be working as I intended. Just the previous approach was fine. Using void was more or less fine. Okay, now decimal number is 21. 21 mod 2 is 1, so we return 1, 0, 1, 0. This digit seems a bit too long, but 1. Decimal number is 40. 1 0 1. Always bothers me more than it should, the lack of groupings of 4 for binary numbers. Now 42 mod 2 is equal to 0, so we're going to have that leading 0 there. 42, let me repeat that. I'm getting distracted. 42 mod 2 is equal to 0. 0 plus 48 is 48, and the ASCII, the character of the decimal character equivalent to the decimal number 48 is 0. So this is going to return a 0 concatenated with what the previous return was. And I'm meaning to look at the function call stack. We're on our 42 is the original number, so we're about to return to the main function. Return that concatenated string. So once we pop that, we're going to be done. Okay. And here we see return to the main function 0 1 0 1 0 1 0. So let me just run through this with returning a leading 0 is silly, but when I return an empty string and rerun this. And let me do quick stepping. Oops, we already got to the end of the main function and it printed 0 1 0 1 0 1. So that is not right. I don't think it's right. Yeah, I'm not sure. Anyways, I suppose that had some value.